Okay, our next paper's title is Statistics-Based Slippage Correction with a Dexterous Robotic Hand. The authors are Zhenyu Lin, Charles Meehan, and John Barras. Speaker today is Zhenyu Lin.
It's not connecting. I don't know why. It was working when I sit down in the coffee break.
Could you hit F5 or something like that to see that? We'll have to ask tech help here. Evan, are you here? What happened?
It's just not connecting.
I tried again.
It was working during the coffee break.
He just did. Is it tightly connected?
Is there a switch or something? Or is it a switch from
Just F8. F8. No? Let's see. This seems to be. Yes. Which one does say then right here? It's not. Change it. Sorry.
Sorry about that. Now I'm not sure if the video will still play. So, my name is Zhenyu Lin, and today the topic of our work is statistics-based slippage prediction and correction with a Dexterous robotic hand. First, I'm going to go over the motivation and also how our work addresses the social need. Between 2019 and 2021, approximately more than 40,000 units of service robot will be sold. So there is a huge need for us to guarantee the robot be able to grasp reliably. And also there is a crucial need for lab-absent people to have the artificial head be able to detect and correct object slippage because they do not have a direct feedback from their robotic hand sensor. And finally, when grasping an object, humans are able to prevent the object from slipping by continuously adjust their hand and apply suitable force. So we want the robot to do the same. We do not want the robot to apply too much force, which may crush the object. As you can see, there's a CareObot 3 service robot handing a cup of drink to the human, and we want the robot to accomplish the task successfully without crushing the object or with even the bottle filling on the ground. So the way we approach this is first we try to collect a data set. We first collected a synchronized haptic and vision data set with 80 experiments. So the tactile data is sampled from a biotech sensor at 100 Hz. And the tactile sensor has 5 modalities. What is most important here, as you can see the biotech sensor over here, the figure B, it has 24 electrodes, which can tell us where the object is contacted with the robotic hand. So, and we also have the vision data with a high resolution. It's just a camera recording what the hand and the object. And also we try to define the sleep moment T star, which is labeled for each experiment. So the first problem is how do we label the moment of slippage? It is not very realistic to label the moment of slippage by just human eye because it's very hard to go to one exact frame to say this is a moment of slippage. So what we're doing is we're implementing a vision tracking algorithm. We use a medium flow tracker because in this case, the movement of the object, it only has one direction, one possible direction. It can only go down. And also the speed is not very fast. So the tracking algorithm has a very high accuracy in this case. So what we claim to be the moment of slippage is that the tracker detects the object has a velocity higher than a threshold. So the reason we try to define the moment of slippage is that we try to understand the statistics of the haptic data around the slippage time T star. We notice that for different electrodes, they will behave differently at the T star, which is the moment of slippage. And for the same electrodes among different experiments, they behave similarly. For example, electrode 3 on middle finger, the electrode data has a trend of going up during the slippage. And for electrode 10 on the thumb, it has a trend of going down. And also for some other electrodes, it may stay the same during the slippage. So what we can do is we try to generate a pre-sleep haptic data sequence for XS, which is just the electrode data along the time interval from T star J minus TA to T star J plus TB, which is a moment around the slippage moment. And notice that the sequence has 120 subsequences because we have 5 fingers, and on each finger there are 24 electrodes. So 5 times 24 is 120. So what we do among all the 80 experiments, we try to take an average of all the sequences because we want to eliminate the variance for just using one single sequence. And the next problem is, how do we determine when a slippage happens? So we can compare the similarity between the sequences. So in the real time, we also have the haptic data sequence, and we try to compare with the sequence that is around the slippage time. So the one way of measure similarity between time sequences is correlation. So we're going back to the traditional statistics method. We're trying to compute the correlation between the real-time sequence to the pre-sleep haptic data sequence we just collected. And also, we will just set an empirical threshold to say, oh, if the correlation is higher than some certain amount, we claim there is a slippage going to happen. Notice that this is not going to be detected after the sleep happens. It will predict that because we're considering the tactile data before the T star J as well. And also, when we detect the slippage, one thing we need to do is correct that. And we need to know how much amount of force we need to apply. So we're utilizing the PDC, which is the flood pressure data, which is from the biotech sensor as well. So we use a DFS 100 digital force gauge to measure the force applied by the fingers, and we try to generate a graph to estimate the force applied by the finger. So as you can see, the PDC to the force applied by the finger, it's almost piecewise linear. So we have a fairly good accuracy of estimating the force applied by the finger. And we also notice that for rigid object and soft object, the vibration of the container is very different. So as you can see on the top, this is a vibration sensor data from the soft container. And on the bottom, it's a vibration sensor data from the rigid container. So based on the vibration data, we can classify the type of the container at the beginning of the experiment. And then we're able to, for the soft container, we should be able to apply a little bit less force because we do not want to crush the object. And for the rigid object, like there's no such kind of threshold. Here is a video demonstrating our algorithm. So without the correction algorithm, as you can see, when we're adding weight to the container will just slip from the hand. And by applying our correction algorithm, the slippage will be predicted, and the hand is able to adjust continuously to correct the slippage. So without the object classification, like whenever the weight is added to the cup, the robot is trying to grasp the object. So this is a plastic cup. As you can imagine, the hand will just crush the object. As you can see, there's clear deformation on the plastic cup. And with the object classification, at the beginning of the experiment, we can notice that, oh, this is a soft container. So we're just applying a little bit of force. And the object there's no deformation in the object. Some of the future directions of our work will be, we should detect the deformation of the object by fusing vision and haptic data. Right now, we're just using the vibration data, so probably there's more we can do. And also, we could generate a more representative pre-sleep haptic data sequence. Remember, we were just taking the average. There are better ways to do that as well. And also, maybe there are some data aggregation and reduction we can do, because using 120 subsequences, that may be too much. And there are some sensors maybe not that important in our slippage detection experiment. So this is all I have for the presentation, and I will happy to take any questions.
Hello. I have actually two questions.
Yeah.
First is where are the electrodes placed? In the fingers or in your head?
So the electrode positions, as you can see,
Yeah, but they are in your head or in your fingers?
On the fingers.
Okay.
So there are one biotech sensor attached to the fingertip of each finger. So there are 5 sensors in total, and each of them is on the fingertip.
Okay. And second was the video that you showed, in that when the object classification was happening,
Yeah.
for the soft object there was still slippage.
That's very correct, because the robot knows that if I'm going to apply additional force, we're going to crush the object.
No, that I understand. I'm
Yeah.
saying is there a solution to that? Because when we hold up even a lighter object, even with a lot of weight, it does not slip.
I agree. That will be a very interesting problem, right?
Wait. If you hold this right, you will then drag it. Take a cup which is very soft, you try to hold it. When you start slipping, you try to squeeze it. Otherwise, it doesn't work. It's mechanical. There's no free feel.
Yeah, follow-up to that is what are you controlling here? Are you controlling the mechanical impedance of the digits?
I'm actually controlling the joint angle or joint velocity of the fingers. This is what I'm controlling. And how I'm controlling that is I have an estimation of the weight. So I have an estimation of the force I have to apply on the object. And we have the force, we know the force to BTC ratio, so we're actually controlling the force. We have a PD controller, which is, the difference is we have a desired force applied to the object, and we have the force currently applied on the object. So there's a PD controller.
Yeah. I can talk with you later. Okay.
Yeah, sure.
Couple of more questions. Take those. Could I ask those people to go ahead and set up?
Hi, have you given any thought to involving the palm in either the grasping task or the sensing of the slipping, rather than just the fingers?
You mean the palm?
Yeah, the palm, sure. Whether it's sensing or participating in the grasping.
Right now it's just the fingers, but
Sure.
it's a very interesting problem, and we're going to do that in the future direction, because think about holding an object. Sometimes the human will move the palm, because if the object is here, we may try to adjust the hand completely. So this is a very interesting future direction for us.
But currently, with the hand we have, if you try to hold the palm, it gets stuck there. So everything depends on how flexible the palm is and what sensor you have on the palm. For that reason, we're looking at other hands that they have, everything is flexible. Because in that robot, if you try to put it in the palm, it gets stuck.
Okay, so the palm's not flexible in your current hand?
Yeah, you see, it's a split component, right?
Yeah.
So if you push it, and we try this, it gets stuck in the palm, and then you cannot, you do that exactly.
Okay.
Our hand is part, I don't know if you know how many bones there are here, it's very flexible.
Yes. Thank you.
One last quick question.
I have one question. How many glass configuration have you considered for the training?
So right now we're just thinking of the initial configuration of the glass is the same. So we're just considering one configuration.
Thank you. Thank you for your talk.